Okay, so let's switch gears now. And today we're going to be talking about the calculations for laboratory. Oops. Let me zoom in just a little bit. So today we're going to be looking at the calculations from yesterday's laboratory, which is laboratory 13, which is the molar volume of gases. Okay, so let's review a little bit about what we know. So we know from the ideal gas law that we used in previous labs that PV is equal to nRT. So where P is equal to the pressure in atmospheres, V is equal to the volume in liters, R is the ideal gas constant, and T is the temperature. Okay, perfect. So, from this information, we can rewrite this equation since we know that the moles are equal to the mass of gas over the molar mass. We can rewrite the ideal gas law as PV is equal to mRT over M. Okay, so just another way of expressing the ideal gas law. In today's lab, we want to find the molar volume of a gas, which is defined as the volume of 1 mole of gas at STP, where STP is known as standard temperature and pressure, which is known as 1 atmosphere, and looking for the temperature at STP, the temperature of STP is 273 Kelvin. Okay. So we want to know the molar volume of a gas at STP. Okay. So the molar volume, which is written as V over N, is equal to RT over P, where T is the temperature of a gas, P is the pressure, V is the volume, and N is the moles of gas. Okay, so you may ask, how are we going to measure all of these things? Well, in this experiment, first and foremost, we are going to take a sample of either sodium hydrogen carbonate or sodium carbonate, and we are going to react it with acetic acid. Okay, so we're going to react it with acetic acid. This in turn will generate gas, which in turn will displace water that we will collect. So the volume of water collected from this reaction is going to be equal to the volume of carbon dioxide produced. Okay, so we have that much information established. Now, from here, we know the volume of gas produced. Now let's talk a little bit about what's going on inside our water collection flask. So inside our flask, we have water, and above the surface, the gas above our water consists of water vapor, this is vapor, plus carbon dioxide gas, which is our product. So then, this water vapor contributes to our total pressure of gas in our collection chamber. So then, we know that the total pressure, which is equal to our atmospheric pressure, is equal to the pressure of water plus the pressure of carbon dioxide. Now, the way that you're going to get the pressure of water, the vapor pressure of water, is there's a table in your lab manual of temperature and the pressure, vapor pressure of water at that temperature. If you look in your lab manual, so just to share, here we go. So as we can see in table 1, we have the vapor pressure of water as a function of water temperature. Does everyone see where we're getting these values from? Does everyone see where we're getting these values from for the vapor pressure of water? Can I get a response in the chat just to make sure everyone can see this table and understand where I'm going to pull these vapor pressure values from? Okay, perfect. So at about 22 degrees Celsius, the vapor pressure is about 19.8 millimeters of mercury, okay? So the atmospheric pressure that we looked up from our local weather source was about 0.98 atmospheres. See the previous lab. So you'd look up your local weather station, you'd look up the ambient atmospheric pressure and convert it to atmospheres, and it was about 0.98 atmospheres. This is equal to the pressure of carbon dioxide plus the pressure of water, which is known to be 19.8 millimeters of mercury. Let's now convert this millimeters of mercury into atmospheres, where we know 1 atmosphere is 760 millimeters of mercury. And that in turn gives us 0.98 atmospheres is equal to the pressure of carbon dioxide plus 0.02605 ATM. So solving for the pressure of carbon dioxide, we get 0.9539. We'll carry through as many digits as possible, which if we wanted to round now, it would be 0.95 atmospheres. So this is the pressure of carbon dioxide, okay? So the volume of carbon dioxide will be measured. The pressure of carbon dioxide we found was 0.95 atmospheres. The temperature of carbon dioxide is going to be equal to the temperature of water. So keeping in mind that our temperatures need to be in Kelvin. Okay. And then in order to calculate the moles, the moles of carbon dioxide, let's focus next on how do we do that? The moles of carbon dioxide, how do we calculate that? Well, we know that sodium bicarbonate and sodium carbonate will react with acetic acid to generate carbon dioxide, water, and sodium acetate. The two chemical equations are shown here. Okay, now what I want you to focus on is that if we start with 1 gram of sodium carbonate and sodium bicarbonate, so my 1 gram of sodium carbonate is equivalent, if we convert that into moles, in 1 mole of sodium carbonate, in 1 mole of sodium carbonate, looking and calculating its molar mass, has a molar mass of 105.98 gram per mole. So that means we start off this reaction and we put into our reaction 0.0094 moles of sodium carbonate. And my question to all of you is, looking at this chemical equation here, how many moles of carbon dioxide do we make per mole of sodium carbonate that reacts? What's our mole to mole ratio? What's our mole to mole ratio? 1 to 1. So that in turn means, and this is really important, that in turn means from 1.0 grams of sodium carbonate, that is equivalent to 0.0094 moles of carbon dioxide produced. So this is our moles of carbon dioxide. We can repeat the same calculation for our 1.0 grams of sodium hydrogen carbonate. In this case, where 1 mole of sodium hydrogen carbonate is equivalent to let me calculate the molar mass really quickly. .84. So in 1 mole of sodium bicarbonate, we have 84 grams. We make 1 mole of carbon dioxide per 1 mole of sodium bicarbonate, which in turn gives us 0.0119 moles of carbon dioxide. Okay, so now that we have the moles of carbon dioxide in each trial, so let's write down what we know so far. The volume of carbon dioxide will be measured. The pressure of carbon dioxide, which is equal to the atmospheric pressure minus the pressure of water, We calculate it to be 0.95 atmospheres. The moles of carbon dioxide for our sodium hydrogen carbonate reaction is expected to be 0.0119 moles of carbon dioxide. The moles of carbon dioxide for our sodium carbonate reaction is expected to be 0.0094 moles of CO2. Okay. So now plugging this into our expression, so we have the volume, we have the pressure of carbon dioxide, we have the moles of carbon dioxide expected from this reaction. So looking at our molar volume equation, which is V over N, that would be equal to the pressure times the temperature. Oops. Sorry, it would be, so PV is nRT. Solving for the molar volume, we get RT over P, which is the ideal gas constant, which is 0.08206 liter atmosphere per mole Kelvin, the temperature in Kelvin, and the pressure in atmospheres. Okay, so continuing on with what data that we have. So our expression for the molar volume, is the volume over the moles. And it should be equal to RT over P. Okay? So one key feature when we perform this experiment is we are not at STP. So what we need to do is if we have our measured volume, temperature, and pressure. So these are experimental. These are our experimental volume, temperatures, and pressures. We need to convert our experimental volume into the volume at STP. Okay? So in order to accomplish that, what we're going to do is we're going to set up our ideal gas law once again. So we know that PV is equal to nRT. R is a constant. So we know that the pressure that we measure times the volume that we measure over the moles that we measure times the temperature that we measure is equal to a constant. Likewise, the pressure at STP, the volume at STP over the moles at STP times the temperature at STP is also equal to a constant, R. So we can relate these two quantities and we can say that P1V1 over N1T1 is equal to the pressure at STP times the volume of STP over the moles at STP times the temperature at STP. Now, the moles are not going to change. So the moles are going to be the same, so we can cancel those out. And we can solve for the volume at STP, where the volume at STP of our carbon dioxide is equal to the pressure that we measure experimentally times the volume that we measure experimentally over the temperature times the temperature at STP in Kelvin over the pressure at STP in atmospheres. Now, once we have the volume at STP, the molar volume is going to be equal to the volume at STP over the moles of carbon dioxide. So, to showcase this in our calculations, let's look at our experimental data. So let's look at our experimental data. So for sodium hydrogen carbonate, when we have 1.0 grams of sodium hydrogen carbonate, what temperature did we measure? What was the temperature of our water that we measured? Let's go through our experimental data now. For 1 gram of sodium hydrogen carbonate, what was our water temperature? What was our water temperature for our sodium hydrogen carbonate trial? You'll have to check your data from the recording or the data that you wrote down in your lab manual. So what was the temperature of our water sample? (17.8 degrees Celsius). Okay, we're going to convert that to kelvins really quickly by adding 273.15. That gives us 290.95 Kelvin. Okay, and that was the temperature was the same for both trials. Okay. The pressure of water is going to be 0.98 atmospheres minus, and now let's look up in our table, at around 18 degrees Celsius, we have a vapor pressure of water of 15.5 millimeters of mercury. We're going to convert that to atmospheres. And that in turn gives us a pressure of water. Oh, sorry, not water. Pressure of carbon dioxide, because we already subtracted the pressure of water. That gives us the pressure of carbon dioxide in this case, which would be, if we complete this calculation, that gives us a pressure of 0.9596 atmospheres. We only retain 2 sig figs. If you wanted to report your final result in your lab manual, you'd write this as 0.96 atmospheres. Okay, perfect. Now, let's look at our 2 trials. For trial 1, the volume. So for trial 1, what was the volume of carbon dioxide collected? For trial 1, what was the volume of carbon dioxide collected? 100.0 mils, okay. We can convert that to liters really quickly. And that gives us 0.1000 liters. What was the volume of carbon dioxide in our second trial? What was the volume of carbon dioxide in our second trial? (86.0 milliliters, which we can convert to liters. Okay, so now that we have all this data at hand, we know that the volume at STP, well, before we do that, if we have 1.0 grams of sodium hydrogen carbonate, to calculate the moles of carbon dioxide expected, we take our 1 gram of sodium hydrogen carbonate, and we know in 1 mole of sodium hydrogen carbonate, we have, looking at our previous calculation, 84 grams. We know that we expect 1 mole of carbon dioxide per 1 mole of sodium hydrogen carbonate. And that in turn gives us an expected moles of carbon dioxide of 1.0 over 84, which gives us 0.0119 moles of carbon dioxide. Okay, perfect. We now have everything we need. So let's calculate the pressure let's calculate the volume at STP. And the volume at STP is equal to, let's pull our equation that we derived earlier, the pressure experimental times the volume experimental over the temperature experimental times the temperature at STP over the pressure at STP. And if we punch in our data now, so for trial one, our pressure is 0.96 atmospheres. Our volume for trial one is 0.1 liters. Our temperature, which we established, was 290.95 Kelvin. Okay, and now the temperature at STP is 273 Kelvin, and the pressure at STP is 1 atmosphere. That in turn gives us a volume STP for trial one equal to 0.090 liters. And then for our molar volume, so for our molar volume, to calculate molar volume, we take the volume over the moles. So we take 0.090 liters divided by 0.0119 moles of carbon dioxide. And that in turn gives us wow, this molar volume is really off. Molar volume 7.56 liters per mole. Let's check our calculations one more time. Recall when we were performing the experiment, I was commenting on how it was quite ambitious that they expected all of the, they expected to collect all of the water displaced in a 100 milliliter graduated cylinder. Really, the collection beaker needs to be more full in the experimental procedure, and there needs to be more water collected, since there is definitely a lot more pressure than a greater volume of gas than the water that was displaced based on the setup in your lab manual. If you filled the water collection flask to the brim and you had a larger place to collect all of the water generated from this reaction, we likely would have observed a greater volume of carbon dioxide collected, and as a result, our molar volume would be a little bit more accurate. Since this is way off from the literature value, the literature value is about 22.4 liters. Anyway, let's continue these calculations for trial 2. So the volume for STP is equal to P1 V1 over T1 times the temperature at STP over the pressure at STP. That gives us 0.96 atmospheres times Whoops, one moment. Allow me to reset OneNote. So completing these calculations for trial 2, the volume at STP is the pressure times the volume over the temperature times the temperature at STP over the pressure at STP, which gives us 0.96 atmospheres times 0.086 liters over 290.95 Kelvin times 273 over 1 atmosphere. And that in turn gives us a volume of STP of 0.0774 liters. And then to calculate the molar volume, which is V over N, we take the moles, which is 0.0774 liters. Sorry, we take the volume over the moles, which is 0.0119 moles of carbon dioxide expected. And that in turn gives us a molar volume of 6.509 liters, which again is way off from the literature value. Any questions so far on this example? Any questions so far on the calculations? So let's just do a run through of where we're at so far once again. Let's just do a quick run through from the start. So first and foremost, we're looking at the molar volume of a gas. The ideal gas law shows us PV is equal to nRT. The molar volume of a gas is the volume of 1 mole of gas at STP. The molar volume is defined as the volume over the moles. We measured the volume of carbon dioxide produced by reaction of sodium hydrogen carbonate and sodium carbonate with acetic acid. The volume of water collected is equal to the volume of carbon dioxide produced. Now, when we collect gases over water, the water vapor, the pressure associated with our gas mixture which is equal to our atmospheric pressure, is equal to the pressure of water plus the pressure of carbon dioxide. We look up the pressure of water in our table to figure out the vapor pressure of water. And from that, if we know the atmospheric pressure, which we can look up online for our area, we can in turn solve for the pressure of carbon dioxide. The temperature of carbon dioxide is just equal to the temperature of the water in Kelvin. Then, to calculate the moles of carbon dioxide, we use our balanced chemical equation and reaction stoichiometry to convert our 1 gram of sodium hydrogen carbonate or 1 gram of sodium carbonate into the moles of carbon dioxide. Now that we have the moles of carbon dioxide expected, we are almost there to calculating the molar volume. So, we measure the volume of carbon dioxide by measuring the volume of water. The pressure of carbon dioxide we can calculate from the atmospheric pressure and the vapor pressure of water. The moles we've calculated from the mass using stoichiometry. And now to calculate the molar volume, we need to convert our volumes that we've measured experimentally into the volume at STP. To do that, we know that the PV over NT is equal to a constant. So we can set PV over NT for our reaction conditions equal to the pressure times the volume over the moles times the temperature at STP. The moles do not change in this process. And as a result, we can solve for the volume at STP to get the following expression. Once we have the volume of STP, we can solve for the molar volume by taking the volume at STP over the moles of carbon dioxide. We've executed on this calculation for our trials for sodium hydrogen carbonate, and we've come to the conclusion that likely there was not enough water available for collection in the setup recommended by the lab manual. We would expect a molar volume of around 22.4 liters, but we're collecting almost a third of that. Probably, as you've noticed when you ran the experiment, a large volume of gas was generated and we were not able to completely collect all of the displaced water in the experimental setup recommended in the lab manual. So this is our complete set of calculations for the molar volume of carbon dioxide for the sodium hydrogen carbonate runs. Let's continue on now with the sodium carbonate runs. So I'd like, first and foremost, what is the temperature of water? What is the temperature of our water for our sodium carbonate runs? What is the temperature of our water for our sodium carbonate runs? Let's look that up in our procedure and from our collected data. What was the water temperature for our sodium carbonate runs? Not the hydrogen carbonate, the sodium carbonate, which we measured when we ran the sodium carbonate samples. Would someone else like to chime in with the temperature from our sodium carbonate runs, which is the second set of trials that we did when we performed and recorded the laboratory? Does anyone have the temperature for our sodium carbonate runs? When we remeasured it, it was a little bit different. When we remeasured the temperature, it was a little bit different. Would anyone like to provide the temperature of water for our sodium carbonate runs? 22.8, exactly right. Okay, let's convert that into kelvins by adding 273, and that gives us 295.95 Kelvin. The pressure of carbon dioxide is going to be equal to our atmospheric pressure, which is 0.98 atmospheres, minus the vapor pressure of water at that temperature, which is approximately 22.4 millimeters of mercury. We can convert that to atmospheres, and that in turn gives us a pressure of carbon dioxide, in this case, of 0.98 minus 22.4 over 760, which gives us 0.95 atmospheres. Okay. The moles of carbon dioxide expected, the moles of carbon dioxide expected, we can get from stoichiometry. So if we have 1 gram of sodium carbonate, we know that in 1 mole of sodium carbonate, we have let's calculate the molar mass really quickly. The molar mass of sodium carbonate is 106 gram per mole. Let's punch that into our calculator. We have 1.0 over 106, which gives us considering that we get 1 mole of carbon dioxide per every 1 mole of sodium carbonate, that in turn gives us for our moles of carbon dioxide, we have 0.0094 moles of carbon dioxide. Perfect. So now we have almost all the data we need. For trial 1, what was the volume of carbon dioxide collected for trial 1? For our first trial of our sodium carbonate run, what was the volume of carbon dioxide collected? For our first trial, what was the volume of carbon dioxide collected? 150 milliliters. That sounds a little more right. Yep. Okay. So then we can convert that into liters. We get 0.150 liters. Okay. We know that the volume at STP is equal to the volume measured experimentally times the pressure measured experimentally over the temperature measured experimentally times the temperature at STP over the pressure at STP. So plugging in numbers, we have 0.15 liters times 0.95 atmospheres over, let's look up the temperature, 295.95 Kelvin times the temperature at STP, which is 273.15 Kelvin, over the pressure at STP, which is 1 atmosphere. That in turn gives us a volume at STP of 0.1315 liters, which we can round to 0.13 liters. Now to calculate the molar volume from trial 1, so to calculate the molar volume from trial 1, we take the volume, which is 0.1315 liters, over the moles, which is 0.0094 moles of carbon dioxide, which in turn gives us a molar volume of 13.99 liter per mole, which we round to 14 liter per mole. Still not the most accurate. Likely we were not able to collect all of the carbon dioxide gas generated, nor measure the amount of displaced water fully using the setup provided by the lab box. If we had a larger collection vessel and if we filled the water collection vessel to the brim, we likely would have had more accurate results. Or we could have used a smaller mass of sodium carbonate or bicarbonate. Okay, let's do one more calculation. What was the volume of carbon dioxide collected for our second trial? What was the volume of carbon dioxide collected for our second trial? $98 milliliters, which we in turn round to 0.098 liters. Solving for the volume at STP, we have V1P1 over T1 times the temperature at STP over the pressure at STP, which in turn gives us 0.098 liters times the pressure, which we calculated in this case to be 0.95 atmospheres, over the temperature, which is 295.95 Kelvin, times the temperature at STP, which is 273.15 Kelvin, over the pressure at STP, which is 1 atmosphere. And that in turn gives us the following result for the volume at STP for trial 2. That gives us a volume of 0.0859 liters. So to calculate the molar volume for trial 2, that in turn gives us 0.0859 liters over 0.0094 moles, which gives us a molar volume of 9.14 liter per mole for trial 2 of our sodium carbonate run. So we've showcased the calculations of how to calculate the volume at STP and how to calculate the molar volume of carbon dioxide generated from the reaction of sodium hydrogen carbonate to sodium carbonate. Are there any other questions? Are there any other questions on the calculations for this laboratory? Any other questions? You should have everything you need to complete the report for laboratory 13 from this lab lecture.